Okay, so this is just going to be another video with just some more practice problems on conditional applications where we'll solve them using trees. And since, again, we've done a few of them, I'm going to go through a little quicker this time, the next few examples. Alright, so this is actually going to be over the next couple pages of notes in your 7.5. This finishes up, we'll finish up part 2 of the 7.5 notes. Alright, so, getting to my example. A health study. Alright, so we're doing a study that's tracked a group of 5 people. A group of people over 5 years. Alright, and we're studying smokers. Alright, we have 20% of those in the... So I don't know how many's in the study, but I know 20% of them were classified as heavy smokers, 30% are light smokers, and 50% of the people in the study were non-smokers. During the 5 years, right, during the study, 10% of the heavy smokers died, 8% of the light smokers died, and 5% of the non-smokers died. And so it's a little subtle, but those last 3 events were conditional cases. Alright, all of these percents here, these probabilities, are conditionals. Alright, this 10% is not 10% of everybody. It's only 10% of the heavy smokers, right? Which isn't everybody, right? Only 20% of the people in the study were heavy smokers. This 8% represents just the light smoker. So given they were a light smoker, 8% of them died, which again, the light smokers were only 30% of the study. And the last ones were the non-smokers. Given they were a non-smoker, 5% of them died during the study, which is our bigger group, right? Non-smokers were 50% of the study. Alright, so first we're our classification of people. Alright, our study. Alright, what we're studying, smoking. I'm assuming is what they're studying. And then what they're looking at here is whether they died or not. And then all outcomes. Alright, during the study. So they're studying basically the death rate of people who are heavy smokers, light smokers, comparing them to non-smokers. So there are 3 classifications in the study. Heavy smokers, light smokers, and non-smokers. So there's going to be a set of branches here that has 3. 1, 2, 3. Right, heavy smoker for H, light smoker, and non-smoker. So H stands for heavy smoker, L stands for light smoker, N stands for non-smoker. And then I'm just going to go ahead and set my tree up. Either they died or they didn't. So D stands for die, D prime is they didn't die. Right, died during the study, didn't die during the study. Died, didn't die. Died, didn't die. And again, it depended on which group they were in, it had different odds of dying or not dying, right? These are my conditions on my tree. Alright, well, the classification, when not everybody in the study was a heavy smoker, right? Only 20% were heavy smokers, so the probability of being a heavy smoker in the study was 0.2. 30% were light smokers, so probability of being a light smoker in the study was 0.3. 50% were non-smokers, so 0.5 probability of being... And again, that's everybody in the study was classified in these 3 ways. And if you look at it, it adds up to 1, right? This adds up to 100% of the people in the study. They are grouped by heavy, light, and non. Right, then there are conditions on the set. Depending on which group you are, you had a different chance of dying or not dying during the 5 years, right, based on the stats. So, given they were a heavy smoker, 10% of them died, so 0.1 is the probability, which means 90% didn't, 0.9. Given they were a light smoker, 8% of them, so remember, 8%, be careful, it's really easy to make a mistake here. If I'm going to make a mistake, this is where it's going to be. Make sure you put 0.08 and not 0.8, because it's a big difference between 8% and 80%. Right? So make sure you're careful, and common mistake is not forgetting to put the 0 in front of the 8 when it's 8%. So 8% of the light smokers died, which means 92, so 0.92, didn't. And 5% of the non-smokers, so 0.05, right, not 50%, 5%, 0.05, died if they were a non-smoker, which means 0.95 didn't, right? 95% of the non-smokers didn't die during the study. Right, then all the outcomes. So probability they were a heavy smoker and died, probability they were a heavy smoker didn't die, and so on. Light smoker and died, light smoker didn't die, and none were non-smokers. Right, and again, those are all and statements. I just leaving out the and symbol. The product implies and, right? A heavy smoker and they died. A heavy smoker, they didn't die. And then you multiply along the path. All right, so the first one, 0.2 times 0.1 was 0.02, which means 2% of the people. Now, these are out of the totals at the end, all outcomes. Out of everybody in the study, 2% of everybody who was being studied were classified as heavy smokers and they died during the 5 years. All right, the next one would be 0.2 times 0.9, which comes out to 0.18. So 18% of the people in the study were heavy smokers that did not die. If you look at this, that's 20%. Right? If you add that up, that's 0.02 plus 0.18 is the 20. So that's all my heavy smokers. All right, this should add up to 30%, 0.3. And again, we multiply 0.3 times 0.08. Comes out 0.24. All right, so that's the probability they were a light smoker and died during the study. 0.3 times 0.92, which would be 0.276. If you add those up, it should add up to 0.3 because those are all of my light smokers, separated by whether they died or they didn't die. All right, then the last one are those who didn't smoke. So 50% times our 0.05 would be 0.025. And then 50% times 0.95 would be 0.475. Which again, if you add that up, that's 50% of the people. Right? Classified by non-smoking. This is the number of non-smokers that died. This is the percent of non-smokers that didn't die. Out of everybody in the study, right? This would be the total. This is my probability distribution. Everybody in the study and their classification and whether they died or they didn't die. Alright, so there's my tree. So again, I went through that fairly fast, but we've done a few of them now, so hopefully you understood where all those numbers come from. Now we're going to use the tree to answer a few questions. Alright, so hopefully I have the tree. I'm going to move on. Alright, what percent? So I've got to remember to write it as a percent of the participants died during the study. So this is looking at everybody in the study, and I want to know what percent died. So they could be a heavy smoker and they died. So that was 0.02, right? A heavy smoker and they died was 0.02. Light smoker and they died 0.024, and non-smoker and they died 0.025. So 0.024 and 0.025, right? Those are all the people that died. Heavy smokers, light smokers, non-smokers. When we add them up, 0.069, remember we want a percent. So that's almost 7% of the people in the study. Alright, 6.9% of that's out of everybody, out of all of the participants, right, everybody, out of the universal case, out of everybody who participated, 6.9% of them died during the 5 years. Some of them were heavy smokers, some of them were light smokers, some of them were non-smokers. Right, that's everybody who died. Alright, the next example. Find the probabilities, this time we just went decimal, that a randomly selected participant, alright, so out of all my participants, right, I just picked somebody who participated in the study, what's the probability that they were a heavy smoker and did not die? Alright, so out of my participants, they were a heavy smoker and they did not die. Well, that's this outcome here, my 0.18. Right, and I just want the probability, I don't have to change it to a percent, so 0.18. Alright, the last case, probability that a randomly selected Find the probability that a randomly selected participant, alright, so a randomly selected participant was a non-smoker that died during the study. Alright, so again, I'm randomly selecting a participant. What's the probability they were a non-smoker that died? So probability that they were a non-smoker and they died. Well, that was one of my outcomes. Non-smoker and they died, 0.025. And we want the probability. Excuse me. Next example. Computer's sticking. Alright, there we go. Alright, my next example. Car manufacturer has 3 different tire suppliers. 45% of their tires come from the first supplier, 35% of the tires come from the second supplier. The remaining tires come from the third. So again, we have 100% of our tires. All right, so if 45 come from the first, 35 come from the second, that's 80% of the tires. That means 20% come from the third guy. They didn't say that, but I know that should add up to 100. The tires come through. So 2% of the tires from the first supplier are defective. 3% of the tires from the second supplier are defective. 5% of the tires from the third supplier are defective. All right, those are my conditionals. Right, it's not 2% of all the tires. It's 2% of the tires from the first guy, right, which is only 45% of the tires. It's 3% of the tires from the second guy are defective, right, which again is only 35% of the tires, and 5% of the third guys are defective, which again is only 20% of the tires. So those are my conditionals. Those go on my second set of branches. So my tree is first, what supplier do we have? And then whether we're defective or not. And then all outcomes. Alright, so there's 3 suppliers, and I'm just going to use 1, 2, 3. So I've got 3 branches again. 1, 2, 3. So I'm just going to use 1 as the first supplier, 2 represents the second guy, and 3 represent the third. And then their tires can either be defective or not defective. And again, depending on which supplier I have a different results, different probabilities. So I'm going to let D be defective and D prime be not defective. So defective, not defective. Alright, so the supplier, the first guy supplies the most. He supplies, so if you're going to pick a tire from this company, 45% chance, it's the first guy, so 0.45. 35% chance it's the second, so 35. The rest come from this guy, right? This should add up to 1, right? One of these guys have to have it. And so these are 0.8, and so this is left with 0.2, right? 20% of the tires come from the third guy. All right, then are my conditionals. If I'm a part of the first guy, if I have a first guy's tire, his odds of having a defective one is less. The odds of the first guy's being defective is 0.02, right? 0.02. Which means 98% are okay, so 0.98. Second guy, 3% of his are bad, so 0.03 are defective if you're the second guy, which means 0.97 are not, right? 97% are not. And then the last guy, 5%, so he is the worst one. 5% of his come out defective, which means 95 don't, right? 95% chance they're okay. Right, and those are all my conditions, right? Given I'm a certain supplier, give me my tire, and I'm assuming that these must be cheaper ones, right? The third guy must give cheaper ones. Right, then all of the outcomes. If I pick a tire from this particular place, I can either be the first guy and it's defective, or the first guy and it's not. Second guy defective, probably second guy not. Third guy defective, and third guy is not defective. Tire. Right, and then you just multiply down. So you're going to take your 0.45 times your 0.02. So the probability you have a tire from the first guy and it's defective is very slim. 0.009, less than 1%. Right, so if you pick a tire from this tire shop, this manufacturer, the probability it came from the first guy and is bad is less than 1%, right? 0.009. Right? Probability the first guy gives you a good tire, right? Not defective. Well, it'll be 0.45 times 0.98, which is 0.441, right? That's 50% of the, or 45% of the tires, not 50%, 45. Right? If you add those up, it adds up to this 45. It's all of the first guy's tires. 44.1% are okay. 0.9% are bad. Right, now do the same thing with the second guy. 0.35 times 0.03, and again, leave it exact, so 0.105. So again, still slim chance, less than 1%. Or no, slightly more than 1%, 1.05%. Right, probability, the second guy gives you a not bad tire, so an okay tire. 0.35 times 0.97 is 0.3395. If those up, those two probabilities add up to 0.35, right? Those are all of the second guy's tires. That's the probability they're bad. That's the probability they're good. All right, now the last guy. All right, so the third supplier, probability you get a tire from the third guy and it's bad, well, that's 0.2 times 0.05, so it comes out 0.01. Right, so 1% chance. And that means third guy gives you a non-defective tire, 0.2 times 0.95, which is 0.19. Right, which again, if you add those up, that adds up to 0.2. That's 0.2, which these are all the tires that come from the third guy. You have a 1% chance it's a bad tire, and the third guy gave it to you. Or you have a 19% chance it's fine. Right? Third guy gave you a fine tire. Right? Those are all of my outcomes. Right? Out of all my tires, those are all the possibilities. So this is the probability distribution. And now answer the question based on your tree. Alright, what percent, so I've got to remember it's a percent. Alright, so what percent of tires are from the first supplier not defective? So what percent of tires, so out of all my tires, so this is out of all my outcomes, they come from the first supplier and they're not defective, well that was this probability here, 0.441, and so written as a percent, 0.441%. Right, so it's the probability that they're the first guy and not defective, which was 0.441, which we want to write it as a percent. So if you're picking a tire, right, you pick a tire from this manufacturer, you have a 44.1% chance it came from the first guy and is a good tire. What percent of tires from the second supplier are not defective? So again, I've kind of highlighted the important phrase here. So the first one was, what percent of tires are this? This one, though, the wording changes. What percent of tires from the second supplier? So we're not looking at any tire, right? We're not looking at the universal case. We're narrowing it down to, I know I've got a tire from the second supplier. So given the second supplier gave me the tire, what's the chance it's not defective? Well, this one is a probability on the tree, and you can go pull it off the tree if you want to. I'm going to set up the formula, because again, I think it's just good rule of thumb to always do the formula. So probability it's not defective, given it came from the second guy. Well, that would be the probability it's the second guy and not defective, over the probability it came from the second guy. Well, probability you got a tire from the second guy was 0.35. And probability it was the second guy and not defective was 0.3395. Which that's using the formula, the conditional formula, right? Given I'm the second supplier, what's the chance the second supplier gives me a non-defective tire? Right, so I divide that out and it comes out to 0.97. Right, which then as a percent, 97% chance. Which should make sense. This is actually one of the probabilities on the tree. Right? If I know I'm the second supplier, right, that's this probability. So it's the probability given that they're the second supplier, the item comes out non-defective. Right? That was the complement to the event they gave me in the problem. Right? They told me 3% of the tires from the second supplier are defective, so it should make sense that 97% are not. If I have a tire from the second supplier, I have a 97% chance it's a good tire. So that's one of the, so it's up to you. If you can recognize that's a probability that's on the tree, you could just go and pull it off the tree. I just always think it's a good rule of thumb to write out the formula and double check it. Alright, just always, because we're going to add to this, we're having a conditional case that's not on the tree when we get to 7-6. That's why my rule of thumb is to always err on the side of caution. But again, you didn't necessarily have to set up the formula. You could have just pulled this straight from the tree. Alright, next example. What percent of tires are? So this is again like the first example. What percent of tires are? There's no condition being placed on it. It didn't say they are from this particular group. It just said what percent of tires are defective. And then I did add this to kind of reiterate. They can come from any of the suppliers. So out of all of my tires, what percent of them are bad? Some of them come from the first guy, some of them come from the second, and some of them come from the third. Alright, so probability there, defective. Well, probability the first guy gives me a defective tire is 0.009, so I want all the ones where I've got defectives. Right, those are the ones I'm going to add up. 009, 0105, and 01. Make sure I can memorize those. So 009 plus 0.0105 plus 0.01, add them up. Which again adds a percent, so almost 3% of the tires. Little less than 3%. 2.95% of the tires are defective. Alright, 2.95%. Some of them came from the first, some of them came from the second, and some of them came from the third. We're looking at all of the tires. If I randomly pick one of my tires, and they can come from anywhere, almost 3%, 2.95% of them are defective. Alright, on your own, what percent are not defective? Which is the complement to that. I will stop there, alright? So that finishes up the tree. So we'll get into part 3 in the next set of videos, alright, which we'll be leaving conditionals behind and looking at independent events. Alright, so independent events in the next video.